So, without delay here, we'll just get going. Take me a bit to get up to speed here to get going and we're comfortable with things. So, radio frequency interference is something that you're going to experience if you're an amateur radio operator. You're either going to cause it or you're going to get it. Anytime there's a radio transmitter or a receiver around, there's a potential for interference to be generated or to be received. So that's a fact of life. However, it doesn't always have to be this way. There are methods to prevent this and methods to deal with interference. And a lot of times it's really quite simple. With radios, when you're dealing with radio frequency interference, you're either going to deal with it at the source or you're going to deal with it where it's being received, at the device that's being affected. Typically, you deal with it with filtering. You've learned about capacitors, you've learned about inductors. These have specific properties. When frequencies are input to these devices, they each have different characteristics. By combining these characteristics in certain ways, we can create devices that either block, pass, or bypass certain frequencies. And we use these methods to either prevent or remove radio frequency interference. So you can get all kinds of interference. Also, radio frequency interference is also sometimes called RFI. You'll see that a lot. And anyone that's dealing with it all the time usually just calls it RFI rather than radio frequency interference. Just like people call vehicles cars instead of automobiles. So you can get interference from another radio station. You can get it from natural static. There are many different phenomena in nature that can actually create electrostatic interference that can actually affect your ability to use your radio receivers. You can get it from other devices, sometimes radios, sometimes just other devices that are using electricity. Because of the way they're designed, the way they operate, they create frequencies which end up being picked up by your receiver. Interference can affect a lot of devices. Just a few to mention are your home entertainment systems. This is the one that you're going to run into the most. This is the phone call from the neighbor. You're coming over my speakers. That's very common. Less common now are television sets because most people have satellite now. And the days of when we used to have a local channel 2, that's gone too. Channel 2 used to be the worst because it happened to be the frequency that was used a lot for 6 meters and things like that. So 6 meters was basically unusable in this town because of channel 2 being transmitted locally. It just was a bad idea to even try. It was so close. Also, there used to be problems with some of the other frequencies in the HF band because the frequencies matched the frequencies inside the TV sets, the old-fashioned TVs, the CRTs, the horizontal flyback transformers and stuff. They're operating at 3 megahertz, 10 megahertz, which are right in the hem bands. So those were also potential problems for acting up. The biggest one is audio rectification, which is your home entertainment system. Audio rectification is probably one of the most common problems that you're going to experience with radio frequency interference dealing with it. It essentially works like this. When you transmit a radio signal from your radio, it travels through the air. That radio signal is then picked up by an object, as say an antenna, and it's fed into your receiver. And this is usually a piece of wire or a conductor. Well, your neighbor has a stereo system, and he has wires connected to it that go to his speakers. So these speaker wires will act like antennas. Radio frequency doesn't know any difference. It sees it as a dipole. So the signal will appear on these lines, and then it gets fed back into your set. And because you have so many capacitors and inductors and different things inside these modern receivers, it has no trouble at all being rectified and becoming an audio signal, and being able to it can actually capture the audio from your transmission, remove the RF component, and once that gets to your audio amplifier, the game's over. The receiver doesn't know any difference between the audio that came from your transmitter and being demodulated by all the circuitry in your radio and what's coming into the stage to be amplified from your tape deck or whatever. So obviously, the way to combat this is to stop it from getting into the set. And this is the most common. You get it with telephones as well. Not so much with the older phones, but the newer ones now got so much electronics in them. All you need is a diode. If you remember your crystal radios, what do you need? A coil of wire and a diode. Do you think there's a coil of wire and a diode in a phone? At least one? Well, there you go. Crystal radio set. You got a problem there too. So the trick is you got to filter it. And we'll be talking about exactly how to do this shortly. So as I was saying, to eliminate interference, you either have to get it at the source or get it at the device that's being affected. It's always best to get it at the source if you can, because if you get the source, that takes care of all the devices. If you have to go to the device that's affected, then you have to go to each and every device. I already got through my whole page just by looking at it. Okay, pension elimination. Okay. Okay, well let's talk about audio rec here. Let's see what I've got here. We talked about audio rec. Okay. I'll go a little bit further into audio rec shortly. I'm going to talk about some other types of interference. Now your radio transmitter has a whole bunch of frequencies inside it. Remember you were talking about how the frequencies are being mixed together to create your final signal. Dave Pitcher was talking about that just last week. Heterodynaming, mixing in the mixer, and so on and so forth. Those frequencies are present in the set, and as they're mixed together, you have all these other frequencies that are generated. Well, these frequencies, some of them are effectively removed during the process, so they never get into your transmitter. Others, not so much. But what can really happen is that once you finally get your last frequency, it can, because of other components in the system, actually start mixing and create products, the sum, the difference, and the originals again. And these can be multiples as well. So it creates what are called harmonics. So a harmonic frequency, have you guys talked about harmonics? Yeah. Yeah, they're multiples of the original frequency. So one of the golden rules of harmonics is that the further you get away from the original frequency, the weaker the actual harmonic is. So the second, third, or fourth harmonic, by the time you get to the 10th or 15th or whatever, it's basically not there. It's not going to get through the filtering. It's not going to affect something. But your second and your third, or first, those can be problems. So you could have a transmitter, say, operating at 54 megahertz, which is in your 6 meter band. Okay? If you double that, that's 108. What device do we know in the house that's 108 megahertz? FM receiver. So it is possible that if you tuned your radio to 108 megahertz near a transmitter on 6 meters that was tuned to 54 megs, you're going to hear them. Now, do you think you can filter that out? Where? You want to do it at the radio, because it's pretty difficult to filter through an FM receiver when it's getting a harmonic. It's pretty hard to do, because there's only 50 megahertz between the two, and filtering and so on. So if possible, you want to stop it from getting out of the transmitter in the first place. Also, HF frequencies, as they are inherently low, they can multiply. So 80 meters can put out harmonics at 40, 20, 10, so on, go right up until they get into the FM bands and other bands that are affected. So again, what you want to do is you want to get rid of this at the source. To do that, I highly recommend that you never set up an HF radio station without installing one of these and keeping it in the line permanently. This is called a low-pass filter. This will block all the harmonics above 30 megahertz. So you can run an HF station knowing that you're not putting out 54, you're not putting out all these other frequencies. And this will probably save you a lot of phone calls. Ernie can tell me a story about those. Ernie had the same problem. I brought one over to him. Problem gone, right? Yeah. They're cheap and they're very. It's good to. Here's the thing with radio frequency interference. You can set up your station, the neighbor sees your antenna, and everything's all fine. But once you've interfered with them once, everything that happens after that is your fault. So, the best thing to do is to make sure that he never knows you're around.
I think they're only I think last time I checked, like $30 to $40.
Yeah, and you can build them. They're fun to build
Where do
too.
you get them?
Yeah, you get them off any of the radio sites, any of your radio supplier sites, Radio World. There's lots of American sites.
Can I have a look?
Yeah, I'll be handing these out.
Okay.
I'll hand them out now as a matter of fact. These are both low-pass filters.
What range did you say? Below 30?
Above 30 megahertz of block
30
setting.
megahertz.
Yeah. Some of these are tunable, so you can actually fine-tune them to get rid of a certain frequency that is irritating you.
This one looks like it is, huh?
This one here is a more advanced version. This one actually can be tuned for each band. So if you had a particular harmonic that was right on and right next to your neighbor and bugging his favorite TV channel, you could literally go to the right one and shift it a couple of megahertz. And even though you couldn't get it down to the level that it wouldn't bother another receiver at that frequency is not being used, your problem is solved. So these are a little more advanced. Filters are fun. Now, most of the time, interference can be taken care of by different types of filters. I will give you two examples here. This is a high-pass filter. Now, we talked about a low-pass filter. This is a high-pass filter. Now, remember I said that you can take interference from either the source or the device affected. Well, this is from the TV days, and FM as well. Since this is a high-pass filter, where do you think it goes? On which device, the transmitter or the receiver? The device being affected or the device itself?
Receiver.
The receiver, yes.
Receiver.
This is particularly effective for a TV set because with a TV, you want to pass frequencies that are higher than what you're transmitting. Therefore, if you put a high-pass filter on it, it automatically gets rid of the frequencies below it. So they don't get to come into your set. So you would put this on the TV to block frequencies below the TV band. And you would put that on your transmitter to keep from generating them in the first place as harmonics.
Just buying one low pass is cheaper than buying a dozen of the small ones.
As I said before, did they see it over there? Yeah. Okay. Right. As I said before, if you can get rid of the source, you get rid of all the problems. If you have to go to each one, then it's a little bit harder. Another very common filter system. This is also, by the way, this is also a bandpass filter. Looks just like a transformer on the old sets when we used to run cable into the back of the rabbit ears. It is essentially the micro version of this. It does the same thing. And they were very effective. Still are if you have a system that's set up to use cable systems. Telephone interference. Same thing again. Comes in on the phone wire. Well, there are filters for that. This happens to be a commercial one. This one is designed, you just plug in one side, plug in the other side, close to your telephone, a short piece of cable. And it prevents the frequencies from getting in to get messed up inside your phone. Takes them off the line. This particular one is made of a capacitor and a coil. So it's a tuned circuit, or it's a filter. Now this particular one also uses what's called a toroid. And I think you might have talked about these when we were talking about transformers. This is the way to make transformers. These are so efficient. One of these guys can handle more power and more stability, and they're more effective than any of the old iron transformers. So it's no wonder that they chose to use these in these. just a toroid alone, placed on a lead-in line, can actually block frequencies.
Isn't that called a balun?
No, this would be like a balun, but it's not a balun. It looks similar to it. That's another thing. Just a toroid on alone, and here's why. If you have current going through a wire, and you place a ferrite core around it, what's going to happen? That current is going to induce another current inside the core of the transformer, of the ferrite, right? Do you remember that from transformers? Well, when it induces a current, what happens when a current flows through? Something else happens.
Creates magnetism.
Creates a magnetic field. And that magnetic field will oppose any change. Therefore, any higher frequencies that are trying to get along the outside of that cable, when they encounter that other magnetic field, they're going to be really knocked down. And the whole filter is going to be powered by the interference. It's pretty cool how that works. So if you take that a little bit further, one of the simplest ways to take care of audio rec in a common stereo system, or a person's home stereo system, is to take a little toroid coil, go right up near where the speakers go into the radio itself, just wrap a portion of the speaker cable around this as much as you want, clip it back in and walk away. That alone will probably end the problem. They're cheap, the neighbor's happy, and done. One of the most common. For heavier duty stuff, you use a bigger coil, but usually not. Surprisingly, I've found in my own personal experience that you can take one of these. Everybody knows, seen one of these?
It's like a carpenter's pencil.
It's a carpenter's pencil, very easy to get. Yeah, take one of these guys, cut it to about 2 inches in length, maybe 3, depending on what you want, and just wrap your speaker lead around it, tape it on 2 sides, and you've just made your own choke coil. And in most cases, this will take care of most radio frequency interference for telephones, as well as the speaker systems. In a lot of cases, that's all it takes. The important thing to remember whenever you're dealing with someone that's getting radio frequency interference is never tell them it's their fault.
Deny, deny, deny.
Never tell them that they have bad equipment, that it's junk. That can particularly bite you in the ass when the guy has a $50,000 stereo system. That will get the door slammed in your face and a lawyer on your doorstep. Don't do it. What you want to do is make sure you know what you're doing when you talk to the person. You know, and it's a good idea if you have an interference situation, to talk with an experienced amateur or someone that knows what's going on, that can either advise you or go with you, because there's a window, and as long as that window is open, you can probably solve the problem very quickly and everybody's happy and so on and forth. But once that window closes, then the neighbor's all upset and now you've got some problems. So the first thing you want to do is be cooperative, be friendly, don't be antagonistic. Never say to them, well, I got a license for my radio, where's yours? That doesn't work either. Okay? Also, because you don't have a license, you have a certificate. That's another story. So, a good idea is to reduce your operations while you're looking for a solution. Show them, okay, I understand that. Okay, well, I'll drop my power. Is that good? Yeah, okay. So for a little while, you drop your power until you can find out, and then at some convenient time, you come in with a solution, and you try to make it simple, in and out. Don't want to be popping open their equipment and doing all these other things, because they will just show you the door. So you want to be doing that. If you can walk in and do something as simple as what I just explained here, not only are they going to be impressed, they're going to be happy. I've actually talked to people over the telephone, instructed them how to do this. They said, well, I've been talking to them, and it's eliminated the problem. So it does work, believe me. Now sometimes things get a little bit more tricky, and that's when you need some more advanced stuff, and you guys probably won't be doing much of this, but people that experiment, that get access to equipment itself, we'll use a whole different array of different types of ferrite beads for things. There are cases where you have a piece of equipment where the problem is because it gets into a little one transistor. And believe it or not, this little tiny little RF bead placed on the emitter or base of the transistor itself, just placed on it, and the problem is gone. But your neighbor's not going to be impressed by the fact you have to open up his set to do it. But just for your own knowledge, these things are possible. These are some smaller, specialized ferrite beads. Very useful stuff. These are some inductors, and of course, capacitors, which you guys have seen before. These happen to be good values for getting rid of RF. There are a couple of other tricks that can be used for radio frequency interference. And this one's kind of funny. You know about resonant antennas. You know the quarter wave is the magic length for most stuff. Well, it's actually possible to create a filter by simply cutting a piece of coax a quarter wavelength long at the frequency that you're receiving, and it will actually give you a notch filter on or about that frequency. And you can put this in a T, say. Do I have my piece here I need? Yeah, here we go. These are a couple I made. Just place it in line with your receiver transceiver, and that just hangs there. And believe it or not, just putting this little guy on a radio here in town, I eliminated a pager 4 miles away from causing an intermod on their receiver. Just by doing that. Isn't radio fun?
That's coming right out of the transceiver?
Yeah, that just sits right in the radio. Okay. This is a piece of open-ended coax.
Yeah, yeah.
You simply cut to around the frequency that you want to get rid of, that you don't want mixing in your receiver, and you just leave that in the line permanently of your VHF receiver. Mm-hmm. And when it encounters a frequency, because the frequency that was interfering was far enough away from the ham band that this was able to do it, to notch it out. It desensitized the receiver at that frequency enough that it didn't get in, and it didn't cause an intermod. It works. This, of course, would be for a higher frequency. Same idea. You create a little T there, and you just use that one instead. As a matter of fact, you could actually probably run both of them in a series and filter out more than one frequency. You had two of them to bother. Theoretically, it's possible. But let's talk about some other interference. So we talked about harmonics. We talked about audio rec. Now, in your receivers, you were talking about overload, receiver overload? That's when a signal is so powerful, it gets into the set, and it just overloads the receiver. It just captures the receiver. This is particularly common in FM, and this will probably be on the test. Everybody know what capture effect is? Okay, FM is one of the most common characteristics of an FM receiver. The FM receiver will grab the strongest signal. If it's got two frequencies that are very close to each other, it will ignore the weaker one and latch on to the stronger one. So depending on how good its filtering is, it may actually receive the other frequency more than yours. And not even more than it, it may just completely remove it from being heard. It's just like squelch. It just locks onto it. Very common in FM sets. The capture effect is great. Is great when it's used properly because the FM is so quiet. You get the signal in there, grabs it, holds it nice, and nice and clean. But when you've got two signals competing and they're close in frequency, the capture effect can come back and bite you. So receiver overload in FM can be a real problem. But it can happen in any mode. that your receiver is overloaded. Then there's only two ways to deal with it. You either have to desensitize your receiver, and that means losing the ability to receive the signals you want as well, or you got to filter it out. In some cases, maybe this will do it. Maybe not. Maybe something a little more advanced. There's a wealth of information on the internet of filters and things and ideas to deal with every aspect of interference you could think of. The guys have been there, they've done it. So don't be afraid to do some research if you run into a problem. Have you been taught about intermods? Intermodulation? Dave might have covered this a little bit. Okay, there is an effect that occurs, very common in FM systems, but it can happen in others. Remember the golden rule that whenever you mix frequencies together, you get the sum, the difference, and the two originals. Don't forget that. That'll be on the test too. Very important. That's really important to understand mixing and everything else. If you never forget that. Whenever you mix two frequencies together, you always get the two originals, the sum, the difference as well of both frequencies. And then from that, other mixes, you get all the harmonics as well. But those are the main guys. So, here's a situation. You got a frequency. Let's say it's 1, 4, so let's see, I got it written down here. Yeah. 146520. Happens to be a very popular frequency on our FM 2-meter band. We got another frequency a little further up. 146580. Now say that both of these frequencies are being used, transmitted in your area, and you happen to be operating on a third frequency. And that frequency happens to be 146490. Now, doing simple math, how far apart are these? Each group. Oh, we got 20 and 80. 2, 4, 6, 8, 30 kilohertz. And then you got 90 and 520. You got 30 kilohertz. So you got 3 frequencies involved here, and spacing of 30 kilohertz between them. Now, remember sum the difference in two originals? Guess what happens when these two are transmitting? What frequency gets generated along with others? And if these two are transmitting, guess what frequency gets generated along with others? This is a 2-frequency, third-order intermod. And this is the most common intermod, and it will be on the test, that you're going to run into. 2-frequency, third orders. What's going to happen? Okay, you're having a nice little QSO with a friend on 14658. Somebody starts a QSO on 520. No problem. You're far enough away, you don't hear him. Well, he's transmitting. This guy keys up his transmitter. Guess what? You're going to hear both of these guys coming over top of what you're listening to. And if he's not transmitting at the time, they're going to sound like they're on your frequency. But as soon as one of these guys takes off his microphone, one of those frequencies disappears, it's like they weren't there again. And this is going to happen every time. That's because these are 30 kilohertz apart, Asian. And if you do the math, one of the calculations of sum the difference in the two originals is always going to generate this guy.
Sorry, I must get lost. I thought it was 7.
No. 30s. Sorry, 30. This is the most common effect, and these can be any distance apart, as long as they're uniform. So this is your standard 3-frequency, or or sorry, two frequency, third order intermod. Two frequencies, third order. Can go either way. This is the most common, and we could, if we had a couple of radios, we could demonstrate it right here, right now. It's very easy to do. Get three handhelds. One transmits on this one transmits on that. You listen on that one, you're going to hear it immediately. Now, intermods have a characteristic that allows people to spot them right away and know them for what they are. And it's this. Not only will you hear the content of both of these transmissions, but the audio will be probably twice as loud as they were on their own frequency because of a multiplication effect that occurs because of the audio frequencies themselves. So you actually end up with a blast with both people talking at the same time. And you might even get a bit of heterodyne too. You might hear kind of a rrr with it too, but it'll be very, very faint because this frequency is not very far apart. You won't be able to hear 30 hertz. Yes? If these two are transmitting, yes. If these two are transmitting, then he's going to get bothered.
What if the two external ones transmitted? There wouldn't be anything there?
No, not unless somebody was over here or over here.
Excuse me, I'm confused. Where are you getting the 30 kilohertz between 520 and 580? Where's the map?
20, 30, 40. Did I say 30?
You said 30, but
I'm sorry.
60, huh?
Yeah, you're right. Sorry. 60 kilohertz with this. What's this one?
That's
30?
30.
Okay, I got the wrong number. Sorry. 5.5.
Thank you.
I meant 5.5.
That was crazy.
My mistake. 5.5.
Thank you.
Yes.
That's probably the slowest number here. I'm going to say the reason for that is because there's an equal amount of distance between the frequencies,
Correct.
which is allowing bleed over to where you're transmitting.
Not bleed over. It's allowing so that when these two frequencies meet together, remember, sum the difference in the two originals. If you do the math, either one of those numbers is going to add up to 146520.
Now that goes with any transmitting.
Yeah, if you see this is called a picket fence effect,
Yeah.
it's going to work everywhere, anywhere.
Okay. And the
Intermodulation, yes.
is a way to detect and push off the side?
No, the intermod is the effect.
The defect.
It's what we call the effect. Like there's an explosion, we say there's a bang. Well, there was an explosion and we heard a bang. So there's an intermod and there it is. It's an effect. It's a name for an effect.
Yeah, we had that in transmitters.
Mm-hmm.
Sorry to ask this. So is it always the same, like 30 kilohertz?
No, it could be, these could be 60 kilohertz apart, these could be 120, they could be several megahertz apart.
As long as it's even.
It's all about the math.
Okay.
If you get two frequencies, you mix them together, if a product is created that ends up on a frequency someone else is using, you're going to get it. Now this is a local effect. This will only affect the receiver within a few kilometers typically. So if somebody's on this frequency on the east end, and this guy's 2 blocks from you, and you're here, it may not happen. Because the one of them won't be strong enough to be captured in your receiver and get past your bandpass filter. But at 2 meters, when you're tuned to 5.8, your rest of your receiver is still pretty wide. You can basically pick up the whole band. But at the last stage, you put your filtering in and say that's this channel, that channel, this channel. But it could still get into your set and start mixing if it's close enough.
So the best way to deal with this would just be to punch your frequency over like a couple of kilohertz.
Correct. Basically go to the next channel. Yep.
You recognize that by the audio being twice as much.
Yes, you will hear both. You'll be twice as loud as the person you were listening to, and you will hear the content of all 3 transmissions all at once.
Must be all mumbo jumbo.
Exactly. Mm-hmm.
It's suddenly really loud. I don't know.
Yep.
Okay.
Yep. So eliminating intermodulation, the only way to do it is either to remove frequency or find a way to specifically filter out one of these. In the case of the pager, I did. I made it weak enough so it couldn't mix, couldn't get into the receiver and cause the problems.
Sorry, remove the frequency
Or filter out one of the stations, if you can. If they're too close and too powerful, you'll have to move. You can only do so much with filtering.
It's not good to live beside another ham operator.
You have, it's part of the game. You can, there are ways, you could suffer and complain about each other, you could compromise, or you guys could go into, could take it as a challenge and play with, and learn all about filtering.
So just continually try to compete with each other for more power so you overpower
Yeah,
the other one.
and be able to filter them out at the same time.
Yeah, just have like a radio arms race where you just concentrate the better filter and power.
I wouldn't recommend that.
Drawing out the next guy.
I actually, you'd be impressed about what you can do with less than 1 watt. It's called QRP, and it's very popular.
Yeah.
You would be
Like
very
this is
surprised. You'd be very surprised. The beauty of QRP, of course, is that you could have a transmitter the size of a cigarette pack, run off a battery. You could walk up to a park bench, take a coil of wire out of your pocket, throw it up in the tree, turn on the unit, put on your headphones, and CW is most common, but you could literally work the world. So it's kind of neat if you think about it. Okay, so we talked about audio rec. So other devices that could be affected. You've got your alarm systems, temperature controls, computers. Computers could be affected, lighting controls, automatic door systems, all kinds of devices. I read a few years ago about a fellow that had an electric wheelchair that he had programmed to operate remotely from a remote control, and he got too close to a taxi, and that chair took off. So, you know, remote control has its pros and its cons.
Yes, I actually, although only slightly related to that because it was like infrared interference. I used to have a little remote control helicopter that had a little infrared remote.
Mm-hmm.
But the TV remote in the room was also infrared, and my little brother actually figured out how to take the control away from me and fly the helicopter with the remote.
The remote control of the
Like
TV.
the TV remote
Oh,
instead
cool.
of the actual controller.
But it didn't fly the way it was supposed to.
Well, not really.
Yeah, that's so.
It almost did. You could get it to go up and like kind of stay level by repeatedly pressing 3. But
Okay, filtering. There, we're going to talk about some different types of filters. You have your high pass, which we talked about. Your low pass,
line 3.
and then we have band pass. And we have notch. I think I've covered most of them. Okay, so we talked about high pass filters. The name high pass. So what frequencies do you think it passes?
Something above a certain point.
Exactly. It depends on how it's designed, but basically it's going to pass frequencies that are higher than the one you want to block. And the same with the low pass. They're going to pass frequencies that are lower than the ones you want to block. A bandpass filter, this is a wideband filter that will pass a wide range of frequencies. So it's not so selective. It actually passes a whole wide range. Now you would want that if you wanted to get rid of some interference from a specific band. A perfect example is that in our work, what we do is we evaluate FM radio stations. So sometimes we go to a site where there's 2 or 3 10,000 watt FM stations. And what we want to do is we want to get a measurement of the carrier level, and then we want to compare that with a measurement of the harmonics or other spurious emissions in the aeronautical bands. The problem is that because we are so close, these other stations can overload the receiver when we tune up its sensitivity and we go just to 109 megahertz and above to look at the nav bands. So we don't care what's going on in the FM band, so we wipe out the whole FM band. We put in a bandpass filter that takes out the whole broadcast band, but doesn't affect the rest of the band. So now we know what we're seeing is real. It's not because of overload. So that's where you would use it when you wanted to get rid of a whole band of frequencies so that you could concentrate on something else. Now the notch filters, what a notch filter will do, unlike a bandpass filter which passes a series of frequencies, a notch filter can either pass a very select frequency or range of frequencies, or it can also, and I forgot to mention this one, this came to mind, a reject filter. This being plus, this being minus, plus, minus. In other words, levels. So what happens is your frequency comes along, it reaches a certain point where it gets past the filter, and it reaches the maximum point, it is best here, and it starts to dwindle down again. So this would cover a range of frequencies, and it would pass them and block everything else. This one would block a very short, small range of frequencies, and it would really knock them out. The notch filter, and that is what this is. That's what this does. But being coax, of course, it's not going to be as tight as that. It's probably going to be more like this. But as long as it gets the frequency I'm after and it's far enough away from what I want to receive, I don't care. It works. Simple and cheap. This one's the opposite. Blocks them all until it gets to the one it wants. Now, the sharper the filters, they cost more money. They get more complicated. You'd use it in specific instances if you had to. Usually, you'd try to use a simple capacitor filter type thing. But in special cases, in commercial stuff and things like that, they need to use sharper filters because they have other frequencies they want to pass that are close by. Thing to remember, high pass filter passes frequencies higher than the ones it blocks. Low pass filter passes frequencies lower than it blocks. Band pass filter covers a series, whole group of frequencies, possibly an entire band. So I call it band pass. Now you can also have a band reject filter, which is what we were talking about when I said a band filter. We had a band, in the case of the FM stations, we wanted to notch them out. That's a band reject filter, which is just the opposite of this. Much bigger notch, blocks the whole band. And the notch filter can either be a reject, it can be configured as a reject or an enhancement. It's one of the two. Okay. How are we doing so far? Everything clear? Okay. Filters. How are we doing? How are we doing for time?
Just about time for a break.
Just about time for a break? Okay, just let me run through my mind, make sure I've covered everything I want to show you. Now, for more information on these particular effects and that, there's an excellent series of documents that are available on the Industry Canada, which is now called Industry Science Economic Development, I think. I can't get the new name in my head. It's too long. And they, before they retired and stopped doing this stuff, they created a section that's under their online resources, radio frequency interference, whole series of pamphlets, which you can download. They're in PDF form for every little instance. Now, we were talking about general radio frequency interference. This is a document called Cutting Through Radio Frequency Interference. It's for general interference. and it will explain a few instances and show you some actual information and diagrams of how some of these filters are constructed, where they might go, how to find interference of different types. This one's not particularly good. It's the one I want. Now there's one that's specifically designed for the operator himself. And it talks more about preventing the problem from an operator standpoint. Highly recommend that you read these and actually print them out and keep them as resource material. They're very good resource material.
Did you say Industry Canada website?
Yeah, it's Industry Canada Spectrum Management is the easier way to catch it. And you'll find quite a bit of information in these pamphlets covering specific types of interference. Because we're talking about harmonics. More information about that too. Some of the channel layouts, different things. Types of filtering, where to put it. Very useful document. Highly recommend that everybody download and keep these around. As your first line of defense. Wrong button. I should also mention, before I finish here, there's a document called the ICES, Interference Causing Equipment Standards. This is a document that the department will use if the situation escalates to the point where they're called in to deal with interference caused by a transmitter or to a neighbor or whatever. The criteria that they follow is that they will then go to the location. They will take detailed measurements of the emissions that are received in the home of the individual. If those levels are above a certain level, then they will assign fault to the operator. If they are below that level, then they will say to the person, it's the fault of your equipment. So in which case they will either tell you to stop operating until the problem can be resolved by filtering or some other means, or reduce your power until such time as you can prove that the problem will not occur again because of some other measures that have been taken. You don't want it to get to that stage, because once the neighbor has had the department point the finger at the operator, that finger will never turn in the other direction again. So be diplomatic, be cooperative, think in advance. Don't do something until, don't, if you can, stay away from linear amplifiers. They're going to get you in trouble. If you live away from neighbors and there's no problems, great. If you're going to put one in, test it, check with your neighbors. If there's a problem, give it back to the guy before you buy it. Yeah. Yeah.
Alan, I knew one individual who was a ham operator, put an antenna up, and he had 20 to 30 complaints that his radio was causing problems.
Mm-hmm.
And the Department of Communication went to look.
Mm-hmm.
There was no antenna going, no wire going to the antenna. The neighbors considered the antenna an eyesore.
Mm-hmm.
So they were complaining that he was causing too much noise. And he had never hooked the antenna up.
Yeah.
Just because you put up an antenna, you'd be surprised how many people.
Yeah, sometimes that happens too.
Now you're a target. Because it's an eyesore, right?
Doesn't have to be a dish.
Yeah, anything, yeah. That's a whole nother. So did I cover everything I need to cover here? Circuits, types of filters, intermodulation. Has everybody got the disc that was sent out? You'll find some more notes on this. Some things I didn't talk about is cross mod. There's a short little section about cross modulation that could also be on the test. Basically everything I wrote in those notes could be on the test. I concentrated on what's on the test. So what I did is I went through and I looked at all the questions in the question bank for a certain thing, and I made sure everything was covered. Okay, so let's take a coffee break, and then we'll talk about station safety.